Ladies and gentlemen, are you ready for the Hofmann rearrangement? Okay. As much as I admire the chemist Hofmann, there's got to be a better name for this reaction. If there's anybody's name on it, there's always a better name. You know that, right? Unless your name's Aldol. We'll talk about that in our last activity today. Okay. So just look at the result and describe what was removed and what it came from. And those two words would be the best name. So what's the functional group that we're starting with here? You're very specific. Primary amide. So in a Hofmann rearrangement, Hofmann elimination's coming up later on a future test. You got to be careful when you say a guy named Hofmann. One, there was a lot of famous Hofmanns. There's one that's still alive today, Nobel Prize winning Hofmann, who's also a playwright. He's a fascinating man. And these older Hofmanns, there were several of those. It's just a common name. And this one, the rearrangement, has to start with a primary amide, and it ends with a primary amine. And what distinguishes this amine based on the original structure? Isn't there something a little less here? One less carbon. And in fact, if you just circle this and put the word DE in front of what that is, the action that describes this reaction is covered. What did I just put a box around? We have a name for that. Don't say anything about nitrogen. In the box, there's no nitrogen. This is part of a functional group, and we have a name for this part. Carbonyl that you removed in this reaction, correct? Does this not sound like a good word for that? Careful. Decarbonylation. That's a good name because this is a carbonyl, isn't it? And I would just say primary amide decarbonylation is a perfect name. That covers everything that happened. I know it's a lot longer than Hofmann, but rearrangement's a big word. I do like the fact that he has rearrangement in the name. It reminds you that during this mechanism, there will be a rearrangement. But that's a nice name. Okay, now we have to use a base, and we have a new pKa. So I'm going to scribble out one of the H's here. And this is a new H that we have to learn a new pKa for our test. And you know, I always find a way of sneaking that on your test. If it's a new pKa, it shows up on your test. It does. I'm just saying. Okay. And I'll just tell you, I'm going to the next question. Why is the pKa below that of an alpha H, which would be pKa equals 20 for a normal alpha H, which is this one, right? Carbonyl. That's an alpha carbon. That's an alpha H. There's your 20. So you're comparing this one to this one, and the only difference is nitrogen versus carbon. And remember, you're making an anion in an acid-base reaction, right? So can you give me an answer for B? Why is the pKa below that of an alpha H, which was 20?
Nitrogen is more electronegative, so it's more stable to have a negative charge.
Oh, I like her answer perfectly. She says the nitrogen's more electronegative, so it forms a more stable anion than carbon. She didn't use those exact words, but she was going there for sure. Okay, so I'm going to write that down. Nitrogen, this is B, is more it would be electronegative than C. So it stabilizes minus better. And your new pKa is 17. Oh, that's a little lower. Yeah, put it with alcohols on your table. So the number's not new, but we haven't had one for an amide ever. So this is our first time we've ever talked about amides being acid. So new pKa alert is in pink. And hydroxide is just basic enough to get an equilibrium amount of these H's off of here. So you have NH with a minus. Okay. Yes, equilibrium. Because the pKa's are very similar, right? You made water. What's the pKa of water? Oh, careful. So actually the equilibrium is slightly unfavorable, right? Why do I say that? Because we usually don't think about larger numbers going towards smaller numbers. That's okay. I can force it to go the way I want when it's close by using Le Chatelier. And what on this page indicates that I used Le Chatelier to make sure I got a significant amount of those H's off. 2 letters on this page. XS. Yeah, just use a large excess of hydroxide. You force equilibrium away from hydroxide. Clever stuff, huh? And what's next? We got N minus, and we have a super electrophile lurking here. Lurking electrophile. That sounds poetic. Bromine, very electrophilic. Reacts quickly. And you have an N-bromoamide. Wow, N-bromoamide. You guys know what N-bromo means, don't you? Uh-oh, you got me worried now. Means bromine on nitrogen, right? Do you want to take a stab at the pKa here? I don't need a number. Just tell me what it's less than or more than.
Less than 17.
I like that, less than 17, because bromine has an inductive effect that stabilizes the minus charge as well. So this next acid base is faster than the first one. Things are picking up is that's what we should say. The rate of the reaction is picking up. And you got a lot of hydroxide. This one's probably a favorable equilibrium, which would also force the other equilibrium, wouldn't it? Well, it is a cool reaction. Nothing earth-shattering yet, right? Okay, we're going the slow way the first time. Okay. So I've got nitrogen with a leaving group on it. Do you agree? Yeah. I've got a nitrogen minus. That's not the best resonance form, is it? What's better, N minus or O minus? So you want to resonate. And then you're going to resonate back, which forces the key second word in the title of the mechanism. Yes. Carbonyl forms. Nitrogen has a leaving group on it. Carbon takes its electrons next door, goes to the nitrogen with the leaving group, and the leaving group does what leaving groups do. It leaves. That is a lot going on there. Let's unpack it. So you're going to have, do you agree you still have a carbon with a double bond to oxygen? Do you agree? We broke the pi here, we remade it here. So that's going to be sticking off the end. O to a carbon Now, how many bonds does the carbon have to nitrogen? Carbon to nitrogen. Talk to me. I'm just tidying this thing up. There we go. How many bonds does the carbon have to the nitrogen? It used to have one, and it gained a second bond with that arrow. So we got two. Yeah, I got a pi as well. There's your N. Br minus up and left. Where's the isobutyl group? It moved over to the nitrogen. Yeah. That is a functional group that you've never seen before, unless you read ahead a little. It's called an isocyanate. Isocyanates by themselves are very useful in synthesis and very dangerous if you're not careful. And this is true of many chemicals. They're incredibly useful. We can't live without them, but you got to deal with them safely. If you want to read about mankind and its hubris, again, part 17,646,725, you read about Bhopal, India, Bhopal. And this was a time in history when I was roughly your age. Just saying, oh, that has no relevance for me anymore. But anyway, you just read about Bhopal, India. Lovely place, but you'll hear about a disaster in the 80s where the isocyanates were like let out into the world. And you know the population density in India in some places is very high, right? So get this chemical factory right beside a major urban area. There's tens of thousands of people died. This is not good news. Chemical safety first, okay? Isocyanates, dangerous, useful, be safe. Okay. This was not the isocyanate from Bhopal. It was I think it was a naphthyl isocyanate, but I'm not sure about that. There was a different R group. That's about it. So this thing has to become these two things. I think we have a lot of work to do is what I'm saying. I see the carbon over here with one oxygen. I see the carbon here has to have three oxygen. That is a hint where you need to go next. Of the chemicals available, which one is best capable of delivering an oxygen to this carbon? And there's a lot of it. OH minus, you're going to use it over and over and over. We've already been using it over and over, right? Don't stop. So HO negative is going to attack. And why did I break that pi as opposed to breaking this pi? Why is that a bad idea? The second arrow is going to go away. The negative charge prefers to be on oxygen because it's electronegativity again, right? So it's pulling strongly, more strongly. And step two, what do you got to start saving some steps, everybody? You do know that you need 2 new H's on nitrogen before the day's over. And keeping in mind, you're going to be doing a lot of catalysis now, where hydroxide is the base in the catalyst and its conjugate partner, it provides protons. What is the conjugate partner of hydroxide? Water. And you know there's more water than hydroxide here. It's aqueous. Yeah. So HOH. Tell me how you're going to get the O minus to become an O neutral again, and the N to get an H from here. It's got to be in green. Here is your carbonyl regenerating. Here's your motivation. If you forgot what carbonate looks like, You should draw it on your test so you know I have to get there. That's carbonate. That's just a spectator. This is 2 minus. Okay. So yeah, you need that carbonyl back, and you need to protonate this nitrogen with the best proton available. Water. You're getting there. O carbonyl, OH, N with a new H, and an IBU. What two functional groups are you seeing in this new molecule? There's 2 functional groups in there. Talk to me. The tertiary amide, and that's a CO2H on the left. What do you always call CO2H? Carboxylic acid. So are you surprised that this thing is called a carbamic acid? You should not be surprised that it's a carbamic acid. And they are unstable. Unstable. They break down in water. They're going, that's what's going to happen to this guy right now. So question. How many oxygens are around this carbon up here? 3. How many oxygens are around the same carbon here? 2. Where'd you get the second oxygen from? Because that's where you're going to get the third from as well. The OH minus. But the fact is, OH minus is not going to attack a carbonyl before it attacks a proton in an acid. So you got to do that first. Acid, base first. And you're not surprised by that. Carbonate has no protons on it when you're done anyway. So the red happens first. Acid base. The green happens next. Nucleophilic attack on carbonyl. Number 2. Green. And I'm pretty sure we'll be able to finish this thing off in the next step. You've got an O minus. Attached to a C. Got an O minus up here. It's got a bond to purple OH. Show that bond. Goes to an NH with an IBU. I got something that's going to look so much like tautomerization. You're going to want to call it tautomerization. You're going to need the acid-base pair again for the final time. And I think you can tell me what the base is going to do. Look at this. What H has to go away? The H on the O, so I need the base to do that. Then I'm going to resonate in to get the carbonyl back. And the N is going to get an H from the conjugate acid of water, of hydroxide, which is water. Sorry, I misspoke. That was a lot of talk. Finish it with a yellow arrow. It goes here and then there and there. How's that? I like it. You need purple hydroxide under the arrow. HOH above the arrow. All one color. It's tautomerization, but it's got an elimination in it. So really, I can't call it tautomerization. It's an elimination. It looks like tautomerizations. But all eliminations look like tautomerizations anyway. So there you go. It's our biggest mechanism of the semester. It's got a lot of little stuff. Nothing's major. That rearrangement's kind of new. Nothing else is really new. So big picture here for you. And we're going to stop our share and end it here.